Hi, welcome to another training video from the HPC Center at the University of Arizona. Today we're going to be talking about managing and optimizing your jobs on the HPC, or tips to improve your workflow and usage of computational resources. My name is Ethan Jan. I'm part of the HPC Consult team here at the U of A, and I say let's get into it. So let me do this. We're going to move this out of the way and jump right into it. So here's what we're going to be talking about today. We're going to quickly go over the prerequisites and overview of this video. Then we're going to talk about job management, both through Open On Demand and on the command line. And then we're going to jump into job optimization, which involves things like resource requests, hardware, testing, and configuration. So what are the prerequisites for this video? So we are going to be assuming some basic familiarity with the HPC system, such as system access, both through SSH in the command line and Open On Demand in the web browser. We're going to assume some basic familiarity about the system layout, such as node types, basically the difference between the login node and the compute nodes. We're going to be talking a little bit about batch jobs, so we're going to need to know what those are, how to submit them, basic stuff like that. We're going to do a little bit of a refresher, but you should be familiar with the concept at least. And lastly, we'll need to know some basic bash commands, such as ls, ssh, basic things like that. And then we'll need to know a little bit of computer terminology, such as CPU, RAM, storage, etc. So if you are a first-time HPC user, or if you are unfamiliar with anything that I just mentioned, I highly recommend that you check out our Intro to HPC course, because that will get you up to speed with all of the basics that you'll need in order to tackle job management and optimization in this training course here. So let's get into it. So managing your workflows on HPC is a crucial component of the research process. It's quite common for users to have dozens to hundreds or even thousands of jobs running simultaneously. So it might be useful to keep track of all of those. Alternatively, you might have a small number of highly resource-intensive jobs. Whatever workflow you use, whether it's many small jobs or a small number of high-intensity jobs, or even if you just have a handful of jobs and you're just trying to start your best practices early, I think that's great. I think regardless of your workflow, you'll have something to gain from this video here. So in this workshop, you'll learn the available tools and best practices for keeping track of your work. We'll learn about tailoring resource requests for all job types. We'll talk about system commands for tracking job performance. And we'll talk about general practices for configuring software to run more efficiently. So this is the broad strokes of what we're going to be covering in this training video. So what is job management? Job management is basically keeping track of all of your active jobs and also previous jobs and how many resources they are utilizing, as well as keeping track of how your previous jobs have performed. So say you ran a job last week and it took maybe 10 hours to run, and this week maybe it's taking 15 hours to run, and you want to know why. Also, awareness and adherence to best practices is part of job management. And why is job management important? So first of all, it helps you keep your work organized. As researchers, it's important to keep track of all of the different things going on, so keeping your work organized on the HPC is going to be a very important part of your overall research process, as well as a very important part of how you use the HPC. It'll also help you have a clearer understanding of how the HPC works. If you're undergoing job management best practices, this means you're aware of the different components of the HPC and the different tools at your disposal. If you're not using job management best practices, you might be unaware of some of the tools that might make your life easier. Overall, it will help you improve your research throughput by keeping everything clean, by managing your jobs effectively. You maybe be able to run more jobs or run better jobs by learning some of the best practices that we'll discuss here. And also, what is job optimization? So job management is one thing, job optimization is slightly different. It often means requesting the optimal amount of compute resources. And what do we mean by optimal? We mean not too much, not too little, not too hot, not too cold, right? If we're throwing way too many resources at a particular job, then we're wasting our CPU time allocation, or we're hogging resources that might be then underutilized when other researchers could be using them. Or also not using too little. If we're using too little resources in fear of burning through our allocation, then we might not be actually using it the most effectively. If we have a few more CPUs on a particular job, we might actually get more out of it. And it requires understanding your compute needs. So everybody's compute needs are different. Everybody's project is different. So you are the only one who can understand your compute needs. So it's best to go ahead and think about those needs and how you might request resources in an optimal way. Another aspect of job optimization is configuring and or executing your software to use those resources most effectively. A lot of software can detect and utilize the many CPUs that are available on the HPC. However, not all of it can do it automatically, and that means it'll need input from you in order to execute that program in a way that utilizes the resources that you have provided to it. And why is job optimization important? So, of course, you'll want to run your jobs faster or larger. Maybe you have a particular analysis that you would like to scale up to a larger database. This will help you do such a thing. You'll also use your CPU time allocation more efficiently. So some groups have a handful of students that all use the HPC, and you'll want to make sure to use it in such a way that all of your group members can get their research done. So you don't want to hog it, or maybe you have a group member who's maybe using too much and you want to show them this video to say, hey, maybe you can use your jobs a little bit more efficiently so that the rest of us can run something. So basically just sharing the resources is a really important aspect of the HPC. Whether it's with your group members or with, even if you're not using your entire CPU time allocation, if you have a large number of unused processors in your jobs all the time, then those processors are unavailable to the other researchers. So we just want to make sure that our HPC system produces as much research as possible. And yes, so freeing up idle resources for other HPC users. So, job management. Basically, how to keep track of and get information on your jobs, both current jobs and jobs that have run in the past. So, there are two main modalities for interacting with the HPC. The first one is, you may use just one or perhaps both, depending on your needs. The first one is the graphical web browser called Open On Demand. You can access this at ood.hpc.arizona.edu. This is also a very common tool, so if you are watching this from another university, there's a pretty good chance that your HPC system has something very similar. There's also the command line interface, which you can use SSH in order to access the cluster and then navigate through using bash commands. So, job management, job types, right? So the Open On Demand is an interactive desktop, and it has graphical apps such as ANSYS and MATLAB, and it can also run servers such as Jupyter and RStudio. So there's a handful of different applications that refer to different job types on Open On Demand. Versus the command line interface, which has basically two job types. There's interactive terminal sessions, which can be accessed with either the salloc command or the interactive command, and that will give you access to a compute node. So what you would do would be to log onto the system, access a login node, and as you know, that should say Genonia or Wenteltrap. If you're on a different HPC system, they might be called something different. But you will see those names for a login node, and as you know, we shouldn't be running jobs on the login node itself. The login node does not have the capability to run strenuous work, so what we would want to do would be to access a compute node. To do that, we would use the interactive or salloc command. And then we can interact with it, which is why it's called interactive. We get input, we can put input into the terminal and immediately receive output based on what we're doing. So that's the first job type for the command line interface. The second is batch jobs, which you might be familiar with. And this involves submitting a script to the scheduler. The scheduler will then run everything that's in your script when it's its turn to run, and then it'll finish up. So the batch job, this is sort of this is sort of an automatic approach where you would type in everything that you would want your job to do in advance, and then it would go ahead and do that. So these are the main types of jobs that you'll encounter on the HPC. So on Open On Demand, what are your available tools for managing your jobs or getting different information about your jobs? There are a few options through Open On Demand, but I would say they're a little bit limited in the types of information they can give you. So what you can see are your active jobs. If you go to the Jobs tab here on the Open On Demand browser, you'll be able to see a couple of options that might be helpful for you. You can see your actively running jobs, and you can also see your job composer. So the job composer is where you would put in your resource request, and the active job setting is where you would see all of your currently running jobs. Now, of course, this is a little bit limited because it doesn't show you any previous jobs. It just shows the ones that are currently running or waiting in the queue at the moment. And then you can also see your interactive desktops with this button here, My Interactive Sessions. So, limitations. These are great tools for viewing or keeping track of jobs that are currently running or pending in the queue. However, if we want to view our previous jobs, or if we want to get more detailed information, we have to hop on the command line. So this Open On Demand section is pretty short. It's pretty much over. There's a few tools that we can use, but they are a little bit limited. If you want to get more in depth in your job management and in terms of the amount of information that you can pull out of the jobs, we will need to use SSH on the command line. Okay, so the secure shell is the way that we access the command line and the command line on the HPC. So we will need to log in to do that. So this is a way of accessing the HPC from a terminal window. If you're on Mac or Linux, this is a built-in command. You can pop open a terminal and type in SSH, your username at hpc.arizona.edu, and type in your password, and you'll be set to go. However, if you're on Windows, you'll need to download an SSH client like this one called PuTTY. And this is the logo for PuTTY. So again, we're not going to spend too much time on system access here. If you'd like more information on how to use SSH, I recommend looking into the Intro to HPC workshop or look at our documentation under the system access setting, or heading rather. So moving forward, let's try it. If you've never used SSH to access the system, try it now. Pause the video and follow these steps. As I mentioned, you can go to docs.hpc.arizona.edu, find the page on system settings. Follow the instructions for your system type, and make sure to access the login node. As I mentioned before, you should see either Wenteltrap or Genonia before your username. So review our system layout page if you don't know what that is, and here is what your command prompt will look like when you are on the login node. So you see here this says Wenteltrap. If you see something like at Gatekeeper, you are not on the login node. You will need to type the shell command in order to access the login node. The Gatekeeper is the Bastion host, which is a security feature that prevents outside unauthorized users from accessing it. So if you're an authorized user, you'll land on the Bastion host, and then you can jump on to the main HPC login node, at which point you'll see Puma here, and you'll see Wenteltrap. So if you don't see those two things, you're not on the login node. Okay. So let's recap what batch jobs are. In case you're unfamiliar, let's go through it. Batch jobs are a way to run code automatically without user oversight or even an active connection to the HPC. So once you submit your batch job, you can close your laptop, walk away, and those jobs will continue to either move through the queue or to run, depending on what stage they're in. So just like all other job types, batch jobs are allocated compute resources through the task scheduler called Slurm. So we use something called Slurm in order to keep track of all of the different jobs that are running on the HPC at the same time. Unlike other job types, batch jobs require something called a batch script that determines everything the job will do in advance. The batch script is submitted using sbatch, the name of your script, .slurm, and will proceed through the queue automatically. So here's an example. It has a handful of sections. The first is where you see the exclamation point bin/bash. That's called the shebang. That needs to be in there in order to tell the system that it is a bash script. Bash, batch, similar sounding words. And then this first section in green here is called the directive section. All of these start with the pound symbol and sbatch. So the pound usually refers to a comment, but in this case it allows you to select your resources by putting in these flags. And of course there's quite a few more flags that you can put in, so check out the documentation in order to see a full list of your options. And then the last section here in yellow is the code section, and this just tells the computer what to run. So this is where you would put in your analysis or whatever it is that you want to do in your batch job. So let's talk about how to get more details from our job management process. So Slurm is the task scheduler used by the Arizona HPC, as well as many other HPC systems. And there are two main commands that Slurm provides in order to get more details about your jobs. And pretty much all of the commands that Slurm provides start with the letter S. So the SQ will give you a list of current, either running or pending jobs, and SAccount will give you a list of finished, either completed, canceled, or failed jobs. And unfortunately, the options for either of these things are a little bit different. So we're going to talk about SQ today, but we're not going to get into the details of SAccount. I highly recommend checking out either our documentation page or the official Slurm documentation in order to get a full list of the options that are available to you. But both have many options to get details on your jobs. And here are the links to the Slurm documentation on both of those different commands. So we're going to go through a simple example for the SQ command right now. The command will simply be SQ. The output will have these headings. So the job ID, that will be the number that is associated with your job, the partition that the job was run in, so it could be something like standard or windfall or high priority, the name of the job, the user who ran the job. ST refers to the state of the job, so that would be running or pending for SQ. Remember, SQ doesn't give you finished jobs. The time, so that would be the time that the job was submitted, the nodes that the job was on, and lastly, the node list or the reason. So the reason code would be something like no group minutes left, and that would be something like if you ran out of your group's CPU time allocation for that month, then you would have to just wait until next month when it starts over. And so if I just ran the SQ command, which jobs is it going to spit out for me? Which jobs is it going to give me details on? It's going to give you every single currently running or pending job on the system. So this is going to be quite a lot. So let's try it. In your terminal session where you SSH'd into the HPC, just type the command SQ and hit enter. What do you see? It's going to be quite a long list of jobs, and is this output useful? It might be, it might not be. Depends on what you're trying to do. So we might want to use SQ with a handful of other options. So for example, if I pipe the output of the SQ command into the head command, head will just give you the header, and this tells it to print the top 15 lines of the SQ output. So if you just wanted to see the jobs that are, say, at the top of the queue, this would be a good way to do it. You could also look at the tail of the SQ by doing this, so that would print the bottom 15 lines. If you wanted to get the number of jobs that are running or in the queue, the WC command, this is word count, and the -L option tells it to count the lines. So the number of lines that it outputs would be the number of jobs that are in the queue or running. And you can also pass it other options. So I can pass --user equals $user in all caps. So this is an environment variable that returns the username of whoever put it in, unless you changed it for some reason. So if it were me, it would put out my username. If you were to run it, it would put out your username. So if you just put this into the command line, this will tell you the running and pending jobs that you have submitted. You could also put somebody else's username in there if you wanted to check on a group member or something, for say. Okay, so these are a few options that we can use. Let's move on to, let's just take a look at the output for a second. So here is the output of the command where we pipe the output of SQ into head, and we got the top 15 lines. So at the time that I ran this, this is what it would look like. If you were to run it now, it would be different. So this is just an example to show you what it looks like. So let's look at an advanced example. So let's just go through this slide one element at a time, and we can figure out what's going on. So this is, I actually have this command aliased to a shorter version just so I can get more specific information than the command that we saw earlier. So the basic SQ command gives you only the options that we saw previously. You can also pass different options to the -O. So -O is right here. Whoopsie. -O is right here. So if we pass this type of string to the -O option, it will print out these options that we see here. So I've put arrows in here so you can see which of the options in the command refers to which options over here. So a lot of them are the same as before, but we can see that you're also able to format strings in a way that you might do in Python, for say. So the %10 here tells you that it gives 10 spaces in order to print out the job ID. So sometimes it might get truncated in the original SQ command, but here you're able to give it a little bit more space so that you can see the full output. So if you'd like, you can pause the video here and see which of those options corresponds to which of the headings here. And then lastly, at the end here, -U, $user, as we mentioned, this will pass your username to that option, and it will print out only jobs run by the current user. Or you could swap out $user with somebody else's username, or you could leave it off to get all of the possible options. So other options that you could pass to it include the --state option, and you can say that I maybe want the running or the pending jobs, and that would return a list of only jobs that matched that particular state. You can also give it a --partition in order to specify the name of the partition to look at. So that would be something like standard, windfall, or high priority. And of course, as I mentioned before, there are tons and tons of options that you can pass to SQ. You can look at the documentation on their website in order to get a much fuller list of all of the different options. So this one prints out quite a few more pieces of information, and you can use it to select jobs that are in different states. Okay, so saccount pulls from a slightly different database than SQ does. So SQ will pull from the database of running and pending jobs, whereas saccount pulls from the database of finished jobs. So ones that have either completed successfully, ones that have been canceled by the user, or ones that have failed for one reason or another. And saccount uses very similar syntax and options as SQ, though they're not exactly the same. So for brevity, we're going to skip a detailed example based on the one that we just looked at. You should get the idea, the big picture idea of how it works. So I'll let you go look at the documentation on their website in order to get a full picture of all of the different options. So this will allow you to pull all of the different options that you want in order to manage your jobs. So if there's a particular piece of information you want, go check the documentation and see what option you need to pass to the saccount command in order to get that particular piece of information that will help you manage your job. So one more Slurm command. This one is called scontrol, and it helps you do a handful more things. It can be used to control your jobs. That's hence the name scontrol. First, you would want to get your job ID from a command like sq, and then you can use a command. So scontrol, you pass it a command option and then a job ID. So there are a handful of different options for command. You can suspend, which means that it'll pause a job that is currently running, and resume will resume that job. Hold is very similar to suspend, but it applies to queued jobs rather than currently running jobs. And release is very similar to resume, except again, it prefers to be used for a queued job rather than a running job. And then if you would like to get more information on a particular job, you can use the show job command and then pass it the job ID, which will provide it more detailed information on that job. So if you're interested in any of these, I recommend you pause the video now, give it a try, pull up a previous job from SQ, and then try, for example, just maybe the show job command so you don't interfere with anything that's actively running or in the queue. And if you get, say, a running job and you put show job in there, see what you can get. The show job command also works with jobs that are finished as well. So saccount and sq pull from different databases. scontrol can apply to any job, but you just need to pay attention to which command to use. Okay, so that's scontrol. Once again, if you want a full list of detailed options, go check on the official Slurm documentation. The purposes here are just to maybe inform you that it exists and give you a few basic options that might be useful for you in your job management practice. So let's talk about a few more job management tools. So all the ones that we talked about so far are provided by Slurm. So all of those S jobs, those are provided by SkedMD, and you can find their documentation on the official Slurm website. The ones that we'll talk about now are not provided by Slurm. So we have a handful of commands that our consultants here have created in order to determine how busy the system is. So as a caveat here, if you are from another HPC system, this command might not be available to you. So talk to your consult team to see what options you have for things that might do something like this. So for example, the first one here is nodes busy. This will give you details for the current cluster only. So for example, if you're on Puma and I type nodes busy, it will only spit out information relevant to the Puma cluster. It won't tell me anything about Elgato, and it won't tell me anything about Ocelote. And it'll be graphical information. So you'll see a full list of all of the nodes on that particular cluster, and you'll see a bar graph that shows you how busy those nodes are. So that'll give you a good sense of how busy the system currently is. If it's very busy, you might experience longer wait times. If it's less busy, that might tell you, hey, now's a good opportunity to submit some jobs. The cluster busy command is very similar to the nodes busy command, except it refers to the whole system. So it doesn't matter what cluster I run this on, you'll see information about all three clusters, Puma, Ocelote, and Elgato, in order to get a graphical picture very similar to the details of the nodes, but you won't get quite so many details. It'll just tell you the overall busyness of that particular cluster. And lastly, system busy is another overview of the entire system. Doesn't matter which one you run it on. and it will be text only rather than graphical. So it depends on what your preferences are. Depends on what type of information you're looking for. All of these commands are very useful in order to determine the busyness of the cluster at the particular moment. So if you want to look more into details on your own jobs, you can use this command, past jobs-d. So that will list your jobs from the last n days on the current cluster. So that, again, won't be particular to any state of the job. It'll just print out all of the jobs from the last n days on the current cluster. So SEFF or SEF, you can pass that a job ID, and it refers to any particular job that you've run. So it's less of an overview of all of your jobs and more of drilling into the details of a particular job. And this will give you an efficiency report. So it's a bit similar to the scontrol show job command, but SEFF or SEF here will give you slightly different information. So compare them, try passing the same job to scontrol show job as you do to the SEF report here, and see what different types of information they can give you. And lastly, we have the job history report, and that will give you detailed job info. So it'll give you, for example, the path that the job was submitted from. If you're like, oh man, I know I ran this job, but I can't remember what the folder was that contained it, this is a good thing to look at. If you want to see how long the job ran for, this is good to look at. If you want to see something like how many CPUs or how much RAM was allocated to your job, this is a good thing to look at. So this is, it won't give you information about the efficiency or performance of your job, but it will give you all of the stats that are relevant to how the job actually ran. Okay, so that's it for job management. There's a lot of different ways that we can go about getting information about our different jobs. We can use built-in commands from Slurm, or we can use other commands. So let's recap. In order to see current or pending jobs in the Open on-demand browser, we can use the tools that we saw earlier, the built-in, the buttons that you can go press on the browser. We talked about how to SSH into the system. We talked about how to use Slurm commands such as sq, saccount, and scontrol to view details of all jobs, including running, pending, and completed jobs. There are a handful of other system commands that we just talked about in order to help with job management. And what's next? So now that we have the ability to pull information about our jobs, we also want to learn how to optimize our jobs. In other words, how to get the most out of your jobs and out of your standard CPU time allocation. So why do we need to optimize our jobs? With so many CPUs available on the clusters, why should I bother optimizing my requests? If I can just throw hundreds of CPUs at a particular job, I don't need to worry about the details of how it's using those CPUs. It's just going to run faster, and then I'm just going to finish all of my research lickety-split, right? Well, it's a little bit more complicated than that, of course. So in order to get more out of your allocation, we need to know, first of all, how much of an allocation you have. So each PI group, this is not per user, but per group, gets 150,000 CPU hours per month on Puma. We get 100,000 CPU hours per month on Ocelote, and a handful on Elgato, but these are really the workhorses here. So if your allocation is shared between many users, or if you tend to run out of CPU hours by the end of the month, optimization practices can help improve your research throughput. That means get more jobs done with the same amount of CPU hours. So this is a very important aspect of job optimization. And in addition, we also want to be good community members. We want to respect the fact that there are hundreds of other users on this HPC who all have research that's just as important as our own. And we want to make sure that the University of Arizona HPC community can produce as much research as possible. So if I'm sitting here on 100 CPUs and my job's only using 10, I'm not really being a good community member. I want to make sure that other researchers have access to those CPUs. So if your jobs are allocated resources that go unused, those resources become unavailable to other users, and it can cause longer wait times in the queue in order to produce that research, because there's a handful of CPUs that are just sitting around not being used. Okay, so let's get an overview of what job optimization really is. And there's basically two categories for job optimization. The first is to make appropriate resource requests. And the second is to call the appropriate options when running your software. So in other words, configuring your software the right way. We will spend most of our time on category 1 as it's the most generally applicable. And we'll also discuss some runtime options for certain common software, but of course we can't cover every possible option nor every use case for those softwares. So in terms of job configuration, the recommended practice is to look into the guidelines for your particular software, because there's so many different ones. Okay. And as a quick little note here, it is also possible to further optimize your jobs by developing more efficient code, but that generally falls more under the umbrella of a research software engineer or a research software developer than a typical research software user. Most of the people who use our HPC system fall under the category of a research software user. That is somebody who went and downloaded code from the internet and used it to perform their research. So this is a great method of doing it. This is how I did my PhD, and optimizing the code under the hood can be incredibly detail-oriented, case-specific, and time-consuming. So this is not a crash course on how to become a high-performance computing software engineer. This is rather a course on how to use those softwares in a way that is most applicable and efficient from a user perspective rather than from a developer perspective. Okay. So let's get an overview of how we want to make appropriate resource requests. So the goal of making an appropriate resource request is to match as closely as possible the allocated resources of a particular job with the resources that a job actually needs in order to successfully complete. Now, that means we have to answer two questions. The first is, what are the resources that are available? And the second is, how many do you need to run your job? So let's look a little bit closer at these. The first question, what are the available resources? This is generally a pretty easy question to answer. Each HPC cluster has its list of nodes. Each node has its own properties, and we'll cover those very soon. So this is just going to be a basic bit of information that we should be aware of in order to answer the question of what are my options when requesting resources. The second question, how many do you need to run your job? Well, this one is a little bit of a more difficult question. There's not really some equation that I can say, oh, I'm running a Python script that looks like this, and that means I need 8 CPUs to run it. Unfortunately, that doesn't exist. There's not really an easy way to determine what exact resources a job is going to need in advance. So the main way to find out here is through trial and error or through scaling tests. So we'll cover all of these things. So the first thing that we might need to talk about is, well, how do we submit a resource request? So the first method that we've talked about in terms of interacting with the HPC is the website, Open On Demand. This is in the browser, and the job composer will basically have a preset list of fields that you can go through and look at and enter the information in. So for example, runtime, you can enter the number of wall clock hours the job is allowed to run. You can enter the core count for a single node, so this would be the number of CPUs, and you would also want to be able to enter the memory per core. One very important thing about this, it's not necessarily possible to enter any number you want for these fields. As we know, a node is just a particular computer that is inside of the larger computer cluster. Each computer, just like your laptop, has a fixed number of CPUs inside of it. I can't enter a number that's larger than the number of CPUs that it has. If I wanted more, I could ask for more nodes, for sure, but I would, check out this question here. It says core count on a single node. So we would want to make sure not to go over the core count that is available on the particular node on the particular cluster. So this is why in just a moment we'll go through all of the different options on each of the clusters. And of course this information is also available in our documentation that you can find online. So you're not expected to memorize any of these numbers, but we do expect that you are aware that there are limitations to the numbers that you can put in, and that you know how to go look up the correct numbers that you'll need for your job. And similarly to the core count, the memory per core, this is not just a sliding option. There's only a fixed amount of memory that each CPU has available to it. So if I put in that correct number, then great, I'm going to be good to go. But if I choose a different number, expecting it to just work with that number, I might have some unexpected behavior. So for example, we have high memory nodes. So if you input a number for memory per core that's higher than the option that's available for standard nodes, the scheduler will say, oh, you want a lot of memory. I'm going to send you to the high memory node. And since the high memory nodes are limited in number and also in very high demand, their queue times tend to be quite long. So this is why it's important to be aware of our options for these fields. They're not just sliding scales. They're not just something that we can enter anything into and expect it to work exactly the same, right? So it's important to be aware of the limitations on these particular fields. So on Open On Demand, you're going to have to just enter your information into this web form. However, if we go to the command line, we're going to need to use a different method. So it's going to be batch directives. So these batch directives, you will just be typing them into the batch script yourself. There's not going to be a preset questionnaire listing all of the different options. So this gives you a greater deal of flexibility, but it also makes it maybe a little bit more confusing. So it's important to be aware of all of the different batch directives that exist, and it's important, just as with Open On Demand, to be aware of the limitations that are put on those options. So again, for example, n tasks here, this refers to the number of CPUs that you're asking for, and it's referring, in this case, you would actually be able to put in a number up into the number of CPUs that are in the entire cluster. However, there's another batch directive that's called tasks per CPU, and on this one, you would want to make sure tasks per node, rather, or maybe CPUs per node. You can look up the exact wording of that batch directive in our documentation. As you can see, I don't even have these perfectly memorized because we have the database that we can go look things up into. Okay, but the takeaway here is that we need to be aware of the hardware of the clusters in order to make sure that our requests are valid, right? So we want to fill out the batch directive section with the relevant information. There is a parameter called memory CPU, and this will be set to the default value for a standard node if not specified. So generally speaking, if you're just using a standard node, it's not necessary to actually go in and specify the memory per CPU. This is something that you can specify if you need to request something other than the standard value. However, if we're just requesting the standard value, it's not necessary to actually include that. And again, you can see our documentation for a full list of batch directives in the running jobs section. Okay. So now it's time to talk about what actually that hardware is. So the UA HPC system has 3 clusters, as I've been mentioning. The main largest cluster is called Puma. The next largest cluster is Ocelote, and the smallest cluster that we have is Elgato. And each cluster is built from different hardware, so resource requests in Slurm will need to reflect the different hardware of the particular cluster that you've chosen to submit to. So, as a warning here, I'm going to show you tables with lots of numbers in them. Please don't get overwhelmed. I'm not expecting you to memorize this. I don't have them memorized. Just as a demonstration that there are all of these different parameters that refer to the hardware of the different clusters, and you can find all of this information in our documentation if you need to look it up. So here's Puma. Here we have 3 different node types. So the first column after the headings is the standard nodes, and the standard nodes don't have any GPUs, which is why these fields here are empty. We can see that in the standard nodes, there is 5 gigabytes available per CPU. And we can choose up to 94 CPUs per node, and there are up to 192 standard nodes. So these are basically the things that we'll need to be aware of when we're constructing our batch scripts or when we're inputting information into the Open On-Demand job composer. So the high memory nodes, they're very similar to the standard nodes, but they have up to 32 gigabytes per CPU. So that means a full node has about 3 terabytes of memory. And when I'm talking about memory here, I'm referring to RAM or the memory that's available to the CPU. This is not referring to disk space. All compute nodes have access to the same hardware through the system, so we don't need to worry too much about the disk space when we're requesting a job. Okay, disk space is something that we can manage, but it's not something that is necessarily relevant to composing a job. And lastly, here on the right-hand side, we have the GPU nodes. Also have 94 CPUs per node and 5 gigabytes of RAM, but we also have different parameters here that refer to the GPUs themselves. So if you're going to go through and request a GPU, you would need to be familiar with these options here. Okay, so that's Puma. On Ocelote, we have a very similar setup, but slightly different numbers. Rather than 94 CPUs per node, we have 28, and rather than 5 gigabytes of RAM per CPU, we have 6. So it's important to be aware when you're switching clusters, you might have to change some of these parameters related to the CPU and related to the RAM. And again, you can go look these numbers up. They're available in our documentation. Here is Elgato. We only have 16 CPUs per node and 4 gigabytes of RAM. So these are the different clusters. These are the different parameters for the different clusters. So you can either refer to this slideshow presentation or you can refer to the documentation in order to pull the numbers that you need for your resource request. So big picture here, different clusters, different numbers. Need to be aware of them when constructing your resource request. Right. So as we discussed previously, these are the common fields in your resource request, and we need to know what our options are. So a quick note on CPUs and memory. This is an important aspect of resource requests that might go overlooked. So each compute node has a certain number of processors that are physically mounted on that node. And each of those processors has a memory chip that is physically mounted to that processor. That means the number of CPUs that you request determines the total memory available to that job. And once again here, I'm talking about RAM, not storage space. So the total memory, you're going to follow this little equation. You'll need to know the memory available per CPU, and you'll multiply that by the number of CPUs in order to get the total memory. So if I'm on Puma, remember Puma has 5 gigabytes of RAM per CPU, and I'm requesting a job with 10 CPUs. That means my total memory available is 50 gigabytes. And again, that's RAM, not storage space. So what this means here is that memory is not a continuous scale, and it's not an arbitrary number. I can't just put in any old number I like, right? If I start just making up numbers and putting it in, I'm going to get some unexpected behavior. I might be using more CPUs than I expected. If I say I want a job with 1 CPU and 100 gigabytes of memory, well, that might not work out exactly the way you expected. You might either get sent to the high memory node, or you might get sent to the you might end up with, say, okay, well, 100 divided by 5, that's 20, right? So I might end up with 20 CPUs and end up utilizing 20 times the CPU hours for my allocation than I expected to. So this is important to be aware of. And once again, RAM, not disk space. So know the total value for RAM per CPU for your machine. If using the total memory flag, make sure this equals the number of CPUs times the memory per CPU. And only input allowed values for memory per CPU. Okay, let's talk about optimizing resource requests. Is my recording still going? Yes, it is. Okay. Okay. Now we need to know what our options are. Sorry, we already know now, we just learned what our options are for requesting compute hardware. The next step is to know what the best configuration will be for our jobs. So we know what our options are, but we need to know what options to choose. The answer is basically testing, trial and error, and scaling tests. So as I mentioned before, there's no easy, quick equation that we can use in order to get the exact number of processors that we'll need in order to complete our job. So testing is the way that we'll have to go. So here is a quick diagram, flow chart that we can use in order to figure out, the optimal resource request. And of course, we're going to need to loop back around depending on what the output of our job is. So the first step is to determine the job to run. If you're a researcher, you probably already know what this is. You can make an initial resource guess. And I would say making an initial resource guess, what you want to do is maybe either very slightly overestimate or very slightly underestimate the resources that you need. And of course, there's no way of knowing exactly what it is, so do your best. And if it doesn't work out, that's okay. We'll iterate and figure out what the best options are. So once we run the job, there are a handful of options that might occur. The job might fail. If it fails, we want to examine the error message. Now, of course, there's numerous reasons that the job might fail, and it might be completely unrelated to the resource request. So, little caveat here, if you do have a job that fails, pay attention to the error logs and make sure to update your job accordingly. This might have something to do with the resource request, or it might not. If you get something like an out-of-memory error, then you'll want to increase the number of CPUs that your job is requesting in order to increase the total RAM. Remember that discussion that we had on CPUs and memory, right? So depending on the output of the error message, you'll need to update your resource request or potentially update other aspects of your job in order to make it run successfully. So if the job does go to completion, you might find that it's a little bit slower than you want it to be. And one thing that's good here is to run scaling tests. Basically run a smaller version of the production job that you want in order to determine how many CPUs you'll need. Say you're running a particular analysis on a database, maybe take a slice of that database. Maybe, depending on the size of it, maybe only take 5% of that database. Run it on that 5%, see how many CPUs it's taking, and then scale up accordingly. And of course, the scaling might not be perfectly linear. It's important to pay attention to the algorithm that you're using. So if you know that the algorithm isn't going to be perfectly linear in its scaling, then you might need to give it proportionally more CPUs. So this is all very dependent on the particular analysis that you're doing. So if you find that your job is too slow, the basic idea, increase the number of CPUs. And the amount that you increase it will again depend on the context in which you're running the job. It depends how much faster you want it to go. It depends whether your job is capable of utilizing those CPUs. So remember that. Remember that the ability of a job to use the CPUs is an important factor as well. If my job is only capable of using 16 CPUs, then giving it 32 CPUs isn't going to make it run faster. So, very common question that we get is, hey, I increased the number of CPUs for my job, but it's not actually running faster. What do I do? Well, the idea here is that you want to go examine your software and make sure that you're passing the correct options in order for it to be able to use all of those CPUs. Okay, And let's say you have a successful run that completes in an amount of time that makes sense to you. What you'll want to do after that is not just say, okay, it worked, and then keep going. You'll want to check the efficiency report. And the reason for this is because you want to make sure that there's not a large number of CPUs that are going unutilized. So say you have a successful run, but your efficiency report says you only used 0.1% of the CPU resources available. Well, you might need to go decrease the number of processors that you've requested in order to make sure that you are using your allocation efficiently, right? So it's this process of increasing and decreasing the number of CPUs. And of course, there's going to be a window of acceptable values for this, right? It's not like there's one specific exact request that we can submit that's going to be the absolute best one. There's room for, this is like a fuzzy target that we're aiming at here. And of course, part of the optimization process is not spending too much time on optimization. You don't want to spend weeks and months and years just getting the exact right values here. You want to get it close enough where it's fairly efficient and runs successfully, right? You don't want to spend too much time going from 98 to 99% efficient, right? So be aware of that aspect as well. Okay, so some additional notes here. So job failures can result from insufficient memory or from numerous other factors. So always important to check the logs of your job. Make sure you always go check the error messages, check the system output so that you can understand what's going on there. Another one being if you increase the number of CPUs and the time to completion does not decrease, then your job is not CPU limited. Or if it is, it doesn't know how to use those CPUs. So again, be aware of all of the options that your program has and be willing to reduce the number of requested CPUs to see if that results in a similar time to completion. And if it does, then you can use those CPUs for something else, or maybe somebody else can. And of course, as I just mentioned, you may need to decrease the number of CPUs requested for a successful run in order to obtain an optimal value. So, efficiency reporting tools are an important aspect of this whole process. So once you've run a test job, it's important to view the efficiency report to see how well it utilized the allocated resources. And we talked about these already, but the best two system tools for this are the Slurm Efficiency Report, or SEFF. This gives you CPU and memory efficiency. And additionally, we have the Job History Report, which provides many additional job details. So using these two in tandem can often give pretty good insight as to the next steps that you'll need to take in the optimization process. And we also have one additional online tool. This is called XDMod, and it's available at metrics.hpc.arizona.edu. And this is a graphical interface. So one caveat with Ceph is that it reports the average CPU and memory utilization for a job. So as a job is going about all of the different things that you want it to do, it might need at some point to use a lot more CPU than at a later point. Maybe in the process of writing to disk, it's using fewer CPUs, but in the process of, say, doing a very large matrix multiplication, it is using those CPUs. So be aware that this usage can fluctuate up and down throughout the course of the job, and that the reporting tool here will give you the average CPU and memory utilization. So it is possible to say that you have a Ceph report that says maybe you use 71% of the CPUs throughout the job. That doesn't necessarily mean that the peak was at 71%. It's possible that it actually maxed out at 100% for a little while and then dropped back down, right? So this is important to be aware of. And unfortunately, there's not really a way that we have of getting a fully detailed graph of the CPU utilization throughout the course of a job. This would require monitoring tools that would be a little bit beyond our capabilities, but it's important to check the logs and see what kind of errors are reported so that you can understand what might have happened. So you know what goes on in your job. You know maybe at this point there is going to be a spike in CPU usage. So, it is possible that your job had an out-of-memory error even though the Ceph report says that it was less than 100%. And this is why using information from numerous different sources will help get you the best possible picture of what actually happened throughout your job. Okay. And here's an example of a graph that can be created in the browser tool of XDMod. And there's quite a lot of statistics that it can report for you. And I would say it's a little bit tricky to use, but you might get the hang of it. Just give it a try, go poke around. There's all of these different options that it can give, and it is very powerful. So depends on how detailed you want to get in your reporting. If you want some detailed reports, XDMod is a great way to do it, and it can generate some pretty nice looking graphs like this one. Okay. So the last thing to talk about here is how to configure your software for optimal performance. So with so many different softwares used on the HPC, of course, I'm not going to be able to cover all possible use cases, but maybe some of these ideas can be more broadly applied, and you can go figure out what you need to do for your particular use case. So check with the developers of your software about their recommended practices for parallelization or for multi-CPU modes. Important. Your software may not automatically detect the number of CPUs you provide in your resource request. So this is very common. It might be possible that you request 16 CPUs, but your software is really only utilizing one of them because it doesn't know how to access those other CPUs. So this is an important distinction between, say, an HPC and your local laptop. If I open up my web browser and open up a bunch of tabs, my computer just knows how to use the CPUs that are available to it. It's not going to restrict it just to one. But if I'm writing, say, a Python program on an HPC, then it's possible that that Python program just doesn't know how to use those other HPCs because Python by default is single stream, or in other words, it only knows how to use a single CPU unless that has been specifically coded into the analysis that you're looking at. So again, you may have to specifically configure your software in order to use those CPUs. So, an example. Let's say there's a Python script that you found on GitHub to perform your analysis. It's been written using the multi-processing library, and you want to run the script using 16 processors on Puma. So one note here, the multiprocessing library is a built-in library for Python, and it enables you to do something called shared memory parallelization. So this isn't going to be a deep dive into the different types of parallelization, but it's important to note, at least in this example, that the multiprocessing library, while it's capable of using multiple processors, those processors all need to be on the same node. So if you're running a multi-node job on the HPC, this might involve using different techniques than simply running a shared memory single node yet multiple CPU job. So once again, be aware of these different methods or avenues of parallelization and make sure you're using the correct one. So we want to run the script using 16 processors on Puma. So try it yourself. Let's say we're going to write a batch script. What should the batch directives to request those processors look like? Go ahead and try and write that down. And what should the line of code in order to execute this program using all 16 of those processors look like? So we want two things here. We want the batch directives to request the resources, and we want the line of code in order to execute the program in a way that actually uses all 16 of those processors. So if you want to participate, go ahead and pause the video and write these down in a text editor. Basically, we're writing our batch script for this job. So go ahead and do that now. Okay, I'll assume that you've gone ahead and done that, and we'll move on. So what should the batch directives to request these processors look like? So the main one that we'll need here is simply sbatch dash dash n tasks equals 16. So since we're on a single node, 16 is fewer than the maximum number of processors on a node on Puma. So single node, we don't need to specify anything other than the number of tasks. N tasks equals 16. Of course, there's going to be other things that we need to include in the batch script, but we're just looking for the ones relevant to the processors right now. And what should the line of code to execute this program using all of those processors be? Well, we're going to actually need to invoke something called MPI. So MPI run is the command that will provide 16 processors to Python. So note that we don't simply call python3 myscript.py. This will not run it in parallel. It will only use a single processor. So in order to actually run it in parallel, we'll need to use MPI run. So this is an important aspect of the code configuration that needs to go into the batch script. Okay, well, that's about all we have time for in our job optimization. So let's recap. Let's go over what we've learned so far. So why do we optimize our jobs? We want to use our allocations more efficiently, and we want to allow unused resources to be available for other users on the system in order to increase the efficiency of the entire HPC system. And how do we optimize our jobs? Well, testing, we're going to want to make an initial guess and then revise based on runtime and testing efficiency metrics, as well as configuration, making sure we call the right batch directives and command line options when running our code. So the idea here is we want to not only request the right resources, but tell the software how to use them. All right, well, thank you for watching. This was a good little video. I hope you enjoyed it. I hope you learned something. If you have any questions or you would like to follow up about anything, please contact us. We have a few different methods of contact. We have ServiceNow. This is our preferred method of contact if you have a problem that you would like to work through with us. You can also contact us via email through hpcconsult@list.arizona.edu. And if you'd like to speak to one of us, we also have virtual drop-in office hours every Wednesday from 2 to 4 p.m. on GatherTown. If you want to find that GatherTown link, it's in our documentation. Just click on the support and consulting services in order to find that GatherTown link, as well as learn more about the other services that we offer. Well, thanks for listening, and I hope to see you around.